In this video, we're going to actually compute multidimensional integrals as iterated integrals. So let's do this example. This is the integral y equals -1 to 1. The inner integral is x equals -1 to 1, 10 minus x squared minus y squared dx dy. And again, we're just going to do the inner integral first. So this is the integral y equals -1 to 1. The integral of 10 going from x is equal to -1 to x is equal to 1 is 20. The integral of x squared for x going to -1 to 1, well, the antiderivative of x squared is 1/3 x cubed, and we're going from x equals -1 to 1. So this is -2/3. Y squared is a constant as far as x is concerned, so this is 2y squared. This is a y integral, 20 minus 2/3, the integral of that from -1 to 1 is 2 times 20 minus 2/3. The integral of 2y squared from -1 to 1 is 2/3 times 2. And this is equal to 112 divided by 3. Or another way to think about this is 37 1/3. Now let's do the next problem. So find the surface, the volume of the surface, z equals x plus xy over this rectangle. So now I'm going to do it with the x integral on the outside, just to do something different from the previous problem. So x will go from 0 to 1. Y will go from 1 to 2. And the function we're integrating is x plus xy dy dx. And again, we're going to do the inner integral and forget about the outer integral. So this is the integral x equals 0 to 1. As far as y is concerned, x is a constant. So the integral of x from y equals 1 to y is equal to 2 is just x. The integral of xy from y is equal to 1 to y is equal to 2 is going to be x over 2 times 2 squared minus 1, which is 3. And this, the antiderivative of x is x squared over 2. So then that integral is 1/2 plus 3/2. Again, the antiderivative of x is x squared over 2. So this is 1/2. And so this is 1/2. This is 3/4. So this is 2/4 plus 3/4. That's 5/4. Okay, so this example, similar to the ones that we've already seen, only now we have negative numbers, but I guess we've done that too. So x will go from -1 to 1. Y will go from 1 to 2, and the function we're integrating is xy. So the new thing here is that I've kind of written it like this. This is a new way of writing it. I've used this symbol, I've said what the region is, I've said what the function is, and now I'm making you fill everything else in. So this is dy dx. So essentially, when you're computing a multiple integral, you have to figure out what the iterated integral is going to be. And then you have to compute the iterated integral. The Calc 3 part of this problem is figuring out what the iterated integral is, going from the problem statement, in other words, this, to the iterated integral. At that point, it's just 2 or 3 Calc 1 problems, depending on whether or not we have 2 or 3 integrals. Okay, so this is an integral from x is equal -1 to 1. Now, the antiderivative of xy with respect to y is just xy squared over 2. So in fact, I could have pulled out the x. Okay, so the antiderivative of y squared, the antiderivative of y with respect to y is y squared over 2. And we're integrating from y is equal to 1 to y is equal to 2. So this is 1/2 times 4 minus 1 dx. So 4 minus 1 is 3, so this is 3/2. And now this is the integral from x is equal to -1 to 1 of x dx. You could just compute this to figure this out, but this is an odd function going from -1 to 1. So this is equal to 0. And finally, in this video, I'm going to do an integral, a 3-dimensional integral. So this is new. We've only talked about 2-dimensional integrals, but the definition of a 3-dimensional integral is similar to the definition of a 2-dimensional integral, which is similar to the definition of a 1-dimensional integral. So now our rectangle, or our cube, or our rectangular prism is given by these intervals here, and this is the function that we want to integrate. So I'm going to have z in the outside, so z goes from 0 to 1, y goes from 1 to 2, and x goes from -1 to 1. And we're integrating the function xy plus z dx dy dz. Now, this could represent some sort of hypervolume in 4 dimensions of something, but one really good way to think about a physical interpretation of this integral is with weight density. So let's say whatever we're integrating has weight density x times y plus z. Now, that might be a little weird because there might be negative weight, but you can think along those lines. And so the weight of this rectangular prism is going to be this integral. Like I said, in this problem, the weight density might not be the best thing to think about because it's negative, but maybe you can think about what a negative weight density might mean. Okay, now again, we're just going to look at this inner integral. Okay, so as far as x is concerned, y is a constant. So the integral of x times y from -1 to 1 is equal to 0. So this part of the integral is equal to 0, and we're just left with the z part. Well, again, as far as x is concerned, z is a constant. And so this is 2z dy dz. And we're just going to look at the inner integral. Now, as far as y is concerned, z is a constant. So this integral is just equal to 2z, because we're going from y is equal to 1 to y is equal to 2. So this is 2z dz. The antiderivative of z is z squared over 2. It'll cancel with that 2. This is just equal to 1. Notice also that if we had done this integral in a different order, it would not have worked out as nicely. In particular, if the x integral was on the outside rather than the inside, we couldn't have used this cancellation that made this integral equal to 0 so quickly. So if you don't understand what I'm saying, just do this same integral, but have the x integral on the outside. Because remember, by Fubini's theorem, we can order the integrals in whatever way we want to.